Hi everyone, this is a reflection video based on our POGIL assignment number 3, dealing with Gaussian, part 1. In this part of the POGIL, we really explored just the whole concept of the p-value and t-tests for significance testing for difference of means. And before I sort of proceed with this, I just want to maybe continue what I was saying about the sort of point of these videos in POGIL in general. The idea of POGIL is that in the classroom you're really responsible for your own learning, and so your the amount of effort you put into your POGIL assignment is hopefully you're finding that you're getting that back in what you learn. And so the downside of POGIL is that sometimes students, I've heard this from students here, and I've heard it from other people, is that sometimes students feel like the take-home message of a POGIL assignment may be a little murkier. It's easier when I'm standing in front of you giving a lecture where I give you PowerPoint slides and I say, A, B, and C, and I tell you this is what A is, this is what B is, and this is what C is, and then at the end of it, you at least have a better idea of what you're supposed to take away from the lecture. But the downside is actually learning it and internalizing it happens a lot more poorly when you learn it that way. That POGIL is supposed to lead to a more deeper understanding of the material, which lasts a lot longer and allows you to sort of apply it to other things in the future. So part of why I'm doing these reflection lectures or reflection videos are so I can try to provide some of that structure to give you sort of a take-home message, a way for you to reflect on what you did in the classroom, and hopefully the things I'm saying to you are all things that you picked up during the class, and it's nothing surprising to you, but I can understand how sort of take-home message can be a little murky at times. So hopefully these videos are helping you in that. So I'll move on with this video. For this is POGIL 3, and this is we finished part 1 on September 6th, Friday. Hi everyone. Alright, so here we are. Again, we were talking about the t-test and p-sig and p-sig and p-insig. Let's change this color here. So what I'm talking about, we're dealing with trying to describe the probability that two populations are the same, or that two populations are different based on it really comes down to the overlap of their Gaussian distribution functions. So we sort of talked about p-sig being something that dealt with the probability that they are different. So that comes from the sort of overlapping area here. So we'll sort of go through the various factors that sort of increases this. So as p-sig increases, the probability that they're different increases, and as p-insig decreases, the probability that they're different increases. Hopefully that makes sense. So so we'll go through this a little bit, and again, so if we're looking at two populations of Gaussians here, right, we describe them by a few factors here. We have right, each Gaussian, each population has its own mean, right? So here's mean 1, mean 2. Each population has its own standard deviation. So standard deviation for this population here, standard deviation for this population here. We also want to describe the differences between the two means, okay? And so what we went through this POGIL assignment, we went through and we talked about a bunch of different ways. What happens when you change these parameters, or when we see these things change. And so the first one, what we looked at was what happens when we change the xi, or the means. So you can see, hopefully you can see from this picture here, right? Going from here to here, we've increased our the differences between these means. And if you sort of think about that thing where the previous picture was showing the overlapping areas, right? That in this case, the overlapping areas here is a lot less than it was, say, here, right? And so as this overlapping area decreases, the probability that they're different increases. So we would say that p-sig increases. The other thing we talked about, and forgive my picture here, but hopefully you'll see from this that in this case our s's, s's decrease. Okay. So what that means is the width of both of these decrease compared to these two, right? And so the means did not change, but the widths changed. And you can see, similarly to this here, the amount of area overlapping between these two decreases. And so as that decreases, we say that the likelihood that these are different increases, that p sig increases. And there's one other thing that is a little less clear, and that comes from the data points. And so what we say is, okay, let's say that this data here comes from let's say, we originally sort of showed, let's say you got 3 data points here. Right? You take 3 random measurements, and you get that Gaussian based off of that. Or if we have 3 different measurements here, right? And so we refer to this as n. So n is like the total number of measurements, or sample size. Let's say sample size. And so the idea is that as we increase the number of samples, as long as all the other parameters are the same, our confidence in the results of these are increased, right? And so let's say if you had, instead of 3 samples, let's say you had 6 measurements, so you had 1, 2, 3, 4, let's say 7. Okay, that's a nice round number. So if you take 3 of these measurements, you get a population that looks like this, which fits the same Gaussian. And if you and then you took the same amount for this other set here, you got, say, these measurements there, right? We'd have more confidence in the differences between these two than if we only had 3, the original 3 on each side to begin with. So to summarize what we took home from that, hopefully, we'll find that as we increase the difference between the two means, our p sig increases, and as our standard deviation, the dispersion around that mean decreases, we also increase, right? As those get narrower, we increase. And also as the number of samples increases, it increases. And just one thing to remember is that p sig and p in sig, so these are just the exact opposite of each other. So as the difference in mean increases, the likelihood that the same decreases. Same thing with standard deviation, same thing with that. So the whole point of the first part of this is to help you guys sort of develop an intuition about what kind of parameters increases or decreases your confidence that the values are going to be different. And so then we moved on to another part, and that part we defined this equation that we called t-calc, right? And this t-calc sort of should really correlate with what we found for p sig. So this here is your differences in means. And so as this difference increases, your t-calc will increase. And then we also have the standard deviation here. You see, as the standard deviation increases, our t-calc will decrease, whereas as the number of samples increases, our t-calc will increase. So so hopefully you can see how this all works. And this is so in the book we talk about 3 cases of t-calc, and we're going to get to case 1 and case 3 on Monday of next week. But case 2, this one here, this is called the let's see if I can spell, hopefully not, of means, okay? And this is by far the most commonly used t-test you'll see. All right, and this is just a mathematical way of testing whether populations are the same or different. And what we did was we used this formula. You get a t-calc, and you compare that to the t-table. The t-table here's an example. There's a nicer one in your book that has more than, this is the significance value of 0.95. And that degrees of freedom is the number of values minus the number of averages. So a lot of the ones we had were, let's look at this example here where I said we had 7 here. Let's say you've got 7 measurements for this red one, 7 measurements for this blue one, okay? So that would be your total number of values equals 7 minus the total number of averages, and we have 2 sets of averages here, so that would be minus 2, 7, so, so you got 7 here, and 7 here, so you have actually 14 in total. So your total number of values minus your total number of averages should be, it's a typo, number of averages, okay. So this would give you degrees of freedom of 12, okay. So that would be somewhere in between these two here. Okay, and what we'll find is if tcalc is greater than t critical, then we say that these are significantly different. Significantly different. Okay. And in your book, which I actually showed you when I showed you the confidence intervals, we saw there was other values, right? You could look for t for 0.90, 0.99, but 0.95 is by far the most common. So what we're saying is we're 95% confident if tcalc is greater than t critical, or 95% confident that these things are different. So I'm just going to run through a quick practice problem that comes actually out of some data that I collected a few years back. And this was dealing with, we were doing some tests to try and understand whether carbon nanotubes cause DNA damage. There's some concern about nanomaterials in general being toxic because they're sort of new species that humans have not been exposed to, and they're being incorporated in consumer products. So a group I was working with was trying to develop methods for studying these. And so this is a picture of a cell here. So this is an electron microscopy image, a thin section. And you can see here a little picture, like these nanotubes would be taken up by the cell and sometimes they end up in the nucleus. So we're wondering, does that cause DNA damage? All right, and so what we have is two data points here. We are two sample sets. We got a negative control, which has this value with this standard deviation, and the nanotube exposed, which has this value with the standard deviation. So before I actually go through and mathematically solve it, I just wanted to sort of draw this out and so help you sort of figure out intuitively maybe what you would expect. So if we look at our negative control, the mean is going to be around 4.2, so let's say just a little bit over here, right? And the standard deviation, which remember is the inflection point of the Gaussian, is going to be plus or minus 0.82. So it's going to be around, I mean, these are all rough estimates here, right? Plus S is going to be around 5. Minus S is going to be around, what's that, about 3.4, let's say. Like that. Oops, minus S. Alright, so we can draw a Gaussian that looks like this. So our inflection points are here and here, and our mean, which should be about the highest point, is there. And so we say, ooh. Oh, good gracious, that's not very pretty. Let's try that again. Alright, this is pushing my drawing abilities here. Alright, so here we go. Alright, well, you get the point. Alright, and so nanotube exposed looks considerably different if you look at this, because we have our mean here, which is about 5.5, which is about right here. Let's call that x2. Then this has a pretty large standard deviation, so the high extreme is about, what, 8.6 or so. So put it over here. And then the low extreme would be minus 3, so that would be around 2, something around here, let's say. 2 point something. So this one, if we drew that Gaussian, we get something like that. Looks a little bit better. And so now if we're curious about the overlapping areas here, right, you would think just intuitively, right, the probability that these are different is going to be inversely proportional to this amount of overlapping area. And we see there's kind of a significant amount of overlapping area here. So my intuition would say that these are probably not different, but let's just go through the math and figure it out. Okay. So we need to use this formula here. All right. So our tcalc. Okay. Let's see what color am I on here. Well, let's use yellow. So our tcalc. So tcalc equals, we got our differences in x's. 1 minus x2 divided by square root of s1 squared over n plus s2 squared over n. Alright, and so in this case, did I tell you how many n's? Shoot. Did not tell you the number of n's here. I apologize about that. This case, n equals 5 and n equals 5. So we have total 10 measurements here. Okay. This actually came from a previous example when I was showing the confidence intervals. If you remember way back then, we were doing 5 of each. Okay. So, so we can just plug those numbers in here, and so let's say we got our average value for one of these is 4.24. Our average value for the other, if the nanotube exposed, is 5.51. And then you divide that by square root of 0.662. This whole thing squared divided by the n, which is 5, plus the other one, which was a significantly higher value, which was 3.31, I believe, squared divided by 5. Alright, sorry about that, little technical difficulties. Alright, so calculate this through and you find your t-calc equals, I think it's something, I don't have the number in front of me, but 0.89. And what we want to do is see if t-calc is greater than t-table, right? And our degrees of freedom, remember, is DOF equals 5 plus 5 minus 2 equals 8. Alright, so we go back here, we look at 8. Alright, here's our t-table. You see that t-calc is less than t-table, or t-critical, as you'll sometimes see this. So therefore, not statistically different. Hopefully that made sense to everybody, as this sort of shows you, hopefully you can understand how this works. That's the conclusion you would at least draw from this data set, that we cannot see any evidence that these nanotubes cause DNA damage. So this is actually going to lead right into my Grubbs outlier elimination video, which will be followed up shortly.